Hello everybody, in this lecture we will be solving 1990 IMO problem number 2. It is a combo problem and here is a view of this problem. Let n greater than or equal to 3 and consider a set E of 2n minus 1 distinct points on a circle. So let's start by drawing that circle. And let's identify these points. I will go ahead and name these starting from P sub 0. So P sub 1, P sub 2, and so on. I'll call this guy P sub j, and then maybe this one is P sub I, all the way to, I guess the last entry would be 2n minus 2, because in total I need 2n minus 1 points, 2n minus 3, and so on. Okay, so we have all of our 2n minus 1 distinct points on this circle. Suppose that exactly k of these points are to be colored black. So we're planning to color k of the 2n minus 1 points black. Okay, such a coloring is good if there is at least one pair of black points such that the interior of one of the arcs between them contains exactly n points from E. And then we need to find the smallest value of k such that every such coloring of k points of E is good. Okay, so once we label these points as P sub I and P sub j and so on, we can take, so let's focus on two of the entries, namely P sub I and P sub j. And let's count how many points are between the arcs. Okay, so how many points are in this range and how many points on the other major arc? So the two exceptions are, so Pi and Pj are outside, but how many will be inside this? So obviously that would be I minus j minus 1. In fact, if you don't want to worry about orientation like whether I and j not, if you don't know which one is greater, you can just even take the absolute value. So that's the number of entries on this one. Right. And then this one here, in this portion, we will have, well, in total we have 2n minus 1 points, minus the 2 points I and j, minus all the points between I and j, which is this thing here, I minus j minus 1. Okay, so, and this thing becomes 2n minus 3 plus 1 minus 2. 2n minus 2 minus I minus j points. Okay, so we know exactly how many points between points I and j, not including I and j, of course. We are not counting I and j. And so therefore what we want is to find pairs Pi, Pj of points such that either inside the minor arc or inside the major arc, excluding the points Pi and Pj, we would have exactly n points, right? So we would have n points, either one of this number or the other one, or this number being equal to n, right? So in the first case, we would get, we can call it case 1. In the first case, we would have absolute value of I minus j minus 1 is equal to n, implying that absolute value of I minus j is simply equal to n plus 1. And in the second case, we have 2n minus 2 minus I minus j is equal to n, implying that I minus j is equal to, if you move things around, is it n minus 2? Yeah, I think it is. So that would be n minus 2. So therefore we can simplify everything. We can actually combine these two results, knowing that there are 2n minus 1 points. We can express it in a modular arithmetic notation. So therefore what we have is the following: for I and j in the range 0, 1, all the way to 2, up to 2n minus 2, we have we will need to have, for a good coloring at least, we want to have the absolute value of I minus j equal to either n minus 2, it will be either n minus 2, or if you just subtract 2n minus 1 from it, because I will investigate it in mod 2n minus 1, so let's use the congruent notation. So it would be minus n minus 2, so therefore plus minus n minus 2. Does that make sense? So these two results are equivalent results basically. So that's for a good coloring, the condition that needs to be satisfied for a good coloring. Okay, so now next step is I will color the line segments connecting PI and PJ for which this condition, so this condition here is satisfied, right? Obviously there will be two lines because of the plus and minus signs. So therefore, yeah, okay, let's draw a new picture. So you have this thing. So once you have your points, let's start from, let's say, P0. So I can go n minus 2 to the, oops, sorry for that. So I will identify the point P n minus 2, because n minus 2 minus 0, the indices, the difference between the indices is n minus 2, sure enough. I will connect it with a line, and I'll do the same thing on the other side. So the difference between the indices should be again n minus 2. So if I'm not mistaken, this one should be Pn plus 1 here. And so on. So we'll do the same thing for every single one of them. So P sub 1 will be connected to P sub n plus 2, and that's a 2, and P sub n minus 1, and then P sub 2 will be connected to P sub n, yeah, so forgive me. So there's no points in this range between these two there, because these are happen to be consecutive entries, that's fine. And then here would be P sub n plus 3, and so on, right? I hope that makes sense. So once we connect with these chords such that they are at a distance n minus 2 from each other, for instance, the distance between Pn and P2 is n minus 2. Therefore, the problem, the revised problem is the following. Revised problem, so would simply be as that find the smallest k such that every k element subset, right, subset of E contains at least one pair of points, one pair of points linked by these lines. That's it. So what is the minimal k that will ensure that I will have a line such that the two endpoints of that line are within that subset of E that I'm selecting? And now let's start the construction. Consider the following sequence. So let me change my board marker color actually. So consider the sequence, so let's write that down. So consider I sub 0, I sub 1, I sub 2. So I'm writing it with formality. So consider the sequence of indices. Well, they are taken from, obviously, from this set, 2n minus 2. Okay. And they are defined by the following recursion. So, and I'll explain in a minute what I mean by this. R minus 1 plus n minus 2 in mod 2n minus 1. So what it means is that if you start from an arbitrary index I0, so you can recursively come up with a way to construct these lines on any given line. For instance, if I0 is 0, like we started earlier at P0, so your next entry would be, because I0 is 0 here, So 0 plus n minus 2, so it's just n minus 2 here. So we just go from p0 all the way to pn minus 2. And then in the next step, pn minus 2 will be, well, obviously it will be connected to another point, which will be, so I2, so let me write it actually. So I1 is equal to I0 plus n minus 2, as we said. I2 is equal to I1 plus n minus 2, and so on, in this mod, and so on, right? So I think the best way, well, okay, so having said that, what this will do is basically the following. So you will start from P0, we will go to P n minus 2, and then from here we will go to our next station, which is P2n minus 4, and then I will keep adding n minus 2 to it, right? So adding n minus 2 to it, we will get 3n minus 6, so subtracting 2n minus 1, because we need to investigate in mod 2n minus 1, so 3n minus 6 minus 2n minus 1, is it n minus 5? Or something like that. Okay, so P 3n minus 6, and yeah, I think it's n minus 5. So forgive me if my algebra doesn't work, but that should be the case. And then we will go to the next guy, which is P n I'll just add n minus 2 to this, so therefore it should be 2n minus 7, and so on. So I guess everybody agrees on what we are doing. So when will this stop? Eventually it will stop when we go back to our starting point, right? So you will have a closed polygonal line, if you will, right? But now the question is, will it cover the whole set E, or will it just cover a subset of it, right? So when I'm done, so it turns out that this sequence defined by this recursion will cover all the elements of the set E, all the elements starting from so all these elements up to 2n minus 2, all these indices. It will cover them. So if and only if it will cover this if and only if, what happens? If and only if, obviously, 2n minus 1 and n minus 2 are relatively prime, right? Relatively prime. And it's very easy to establish that 2n minus 1, you can simply subtract 2 times n minus 2 from it to find the greatest common divisor, obviously. And that would simply be equal to 2n minus 1 minus 2n plus 4. That's 3. Okay, so therefore, so this procedure will cover all the points of E if and only if 2n minus 1 is not divisible by 3, right? So if and only if 2n minus 1 is not divisible by 3. That's it. And now, so therefore the resulting polygon will have 2n minus 1 vertices in this condition, and the same number of edges, obviously, and that's good. Okay, in the other case, namely if 2n minus 1 is divisible by 3, so our procedure, our recursive procedure here will stop before covering all the elements of E, right? In fact, it will only cover a third of the elements of E, namely 2n minus 1 over 3 elements. So the first polygonal line will cover this many points. So therefore, there will be 3 what do you say? 3 closed polygonal line polygons, basically 3 closed polygons. I don't think that's called polygons, but so let's say 3 lines. So that together, when we take the union, will give us the whole set. They will visit all the vertices of our set. Okay, so let's simply work on examples, because I don't want to confuse people any further. When we work on an example, you will see it very clearly what I mean. Okay, so consider the first case. 2n minus 1 is not divisible by 3. That's the case for n is equal to, say, 6. When n is equal to 6, 2n minus 1 is equal to 11. So we have a set with 11 vertices. So we have our circle, P0. Yeah, so 3, 4 more. 1, 2, 3, 4. 1, 2, 3, 4. So P1, P2, P3, P4, P5, P6. That's a 6. P7, P8, P9, and P10. So if you guys are ready, let's begin, right? So we first of all, what is n minus 2? So n minus 2 would simply equal to 6 minus 2, which is 4. So that's our differences. So we start from P0 and we go to P4. And then from P4 we add 4. We will go to P8. Add 4 in mod 11. So we will go to P1, 2, 3, 4. P1. Oops. And then at 4 we will go to P5. Then P9. Then P2. P6. P10, P13, I hope that works. Yeah, P3 I should say, then P7, and thankfully eventually to P0. Wow, so that's beautiful, right? So now how does the coloring work? So how many elements should I have to pick at the least so that I know for sure that I will always obtain the endpoints of a given line segment, right? So let's say that we decided to color P0. If actually, let's use a board mark. Okay, so this one. Let's say we color P0. So we pick P0. Therefore, it means that we cannot pick P4, which is directly connected to P0, right? I'm trying to find the smallest here, right? So therefore, I cannot pick P4, so which means I can pick P8. P8 is connected to P1. I cannot pick P1, but I can pick P5. If I pick P5, I cannot pick P9, meaning I can pick P2, and then I cannot get 6, but I can definitely take 10, right? And because I took 10, I cannot take 3, but I cannot take 7 either because they are both connected to P0. So therefore, if I just pick 1, 2, 3, 4, 5 points, none of them, I can never get the endpoints of a line, right? So therefore, I need at least one more point. So therefore, so in this case, when it's not divisible, for instance, the smallest number that I will need will be 5 plus 1, which is equal to 6. But 6 is just n, right? Haha. So therefore, we have an answer for this case. If so let's say therefore the answer would be the smallest value of k, so or I can conclude at the end. Let's conclude at the end. When it's not divisible by 3, then we claim k equals n is the thing. Of course, you can generalize this logic easily on your own. How about if 2n minus 1 is divisible by 3? This case is also very nice. 3 divides 2n minus 1. For instance, consider the case n is equal to, I think, 5 or 4 works. I think 5 works, yeah. So consider n is equal to 5. In this case, 2n minus 1 would be 2 times 5 minus 1, which is 9. Okay, so therefore, let's have our circle again. Let's do it here, I guess. 1, 2, 3. So I need 6 more. 1, 2, 3. 1, 2, 3. Okay, I have my P0, P1, P2, P3, P4, 5, 6, that's a 5, 6, 7, 8, okay. And as again, I will first have to do the coloring. So n minus 2 is simply equal to 5 minus 2, which is 3. Sorry for the handwriting. So therefore, I start from P0, I go to P3, then P6. Oh, I end up back at P0. Therefore, I have to start again at P1, go to P4, P7, P1. I'm done again. And then P2, P5, P8, and P1. And oh, shoot, what am I thinking? I'm high. Come on. Okay, there you go. Yeah. So where was I? Okay, yeah. So P2, P5, P8, P2 again. Whew, okay, so therefore let's start picking the coloring the vertices. So I can pick this guy first. If I pick this guy, I cannot pick P3 or P6 because they are both connected to P0. Then I can pick on another cycle, I can pick P1, but once I pick P1, I cannot take P4 or P7. In a similar way, once I pick P2, I cannot take what the heck is this? P5 or P8. So therefore, three would not be sufficient. Coloring 3 only won't work. So K should have to be at least, in this case, K is at least 3 plus 1, which is 4. Now relating it to N, we realize that this is simply equal to 5 minus 1, which is n minus 1, and that's my guess for this case as well. So K is equal to n minus 1 if 2n minus 1 is divisible by 3. Okay, obviously you can work through the algebra and you can write a more rigorous proof, but therefore the final result is that the smallest value of K for which so let's write that down. Conclusion. So we just proved that the smallest K for which every such coloring, and when I say such, you know what I mean, such coloring of K, come on, of K points is good, let's say equals the following. So it equals n if 2n minus 1 is not divisible by 3, and it's equal to n minus 1 if 3 divides 2n minus 1, and that solves the problem. Hope to see you guys in our next video.